Okay, so I think that's enough for that paper. I did want to talk about that because I thought it was really interesting with respect to some of the other things we're talking about, um, especially some of the physics influenced models that we've been talking about. Okay, the other thing I wanted to talk about today was this article. I believe it's from a Substack, Infinite Faculty Substack. And this is called Symbols, Neural Networks, and Mathematical Intelligence. So this is, again, something we've been talking about earlier in the meeting and thinking about some of these aspects of connectionism and the basis of higher level cognition. And this is a little cartoon showing like a robot formulating equations. Okay, so let's start off here. Recently, a language model found a counterexample to the Jacobian conjecture, a widely known problem in mathematics that has been open for almost 90 years, and which has been somewhat notorious for incorrect proof attempts by mathematicians. So this is going to talk about how mathematicians use large language models and how this affects the field and how this is, how we interpret the things that we can get out of large language models, which is kind of an interesting area because mathematicians have been using large language models, and the question is if a large language model comes up with a proof, how do you evaluate that? And Terence Tao has been doing some really interesting frontier work in that area. The counterexample is remarkable in that, being a relatively simple equation, it fits into a tweet, which is how it was announced. So this is the tweet where it says, "Hello there, the Jacobian conjecture is false. Thanks to my close friend Akil for asking about it, and my other close friend Fable for working during the World Cup final." And then this is the mathematical statement here. If you happen to be literate in some undergraduate level algebraic geometry, Terence Tao wrote a very nice, detailed, and not too technical explanation of the counterexample. So this is the counterexample. This is from Terence Tao's blog. And it's a digestion of the Jacobian conjecture counterexample. So this talks about a little bit about this conjecture using Fable AI. So this is what they were talking about in the tweet. So this is so the notorious Jacobian conjecture can be formulated concretely over the complex numbers as follows: the condition that the Jacobian is a non-zero equivalent, or that df is a non-zero equivalent to f being locally invertible. And also, okay, so let's get down to where it talks about, what's good and bad about this, I guess. So it was recently shown using the Fable AI that the conjecture is false in 3 dimensions, and thus in higher dimensions as well. The conjecture remains open in 2 dimensions and is easy to establish in 1 dimension. The example can be stated completely explicitly, so one can take this equation and one can verify by a brief calculation that df equals -2, and then this is the other part here. While this is an extremely quick verification, the construction presented in this fashion appears like a massive miracle. The polynomial f has degree 7, so a priori the Jacobian df ought to be a polynomial in 3 variables of degree as large as 18, or 3 times 6 equals 18. So the fact that all non-constant coefficients of this polynomial vanish looks like a massive cancellation involving 1,329 equations, which is much larger than the 360 degrees of freedom for a generic degree 7 polynomial map of 3 variables. So finding such a polynomial looks highly unlikely to be located by brute force. This example has since been retroactively explained in more geometric terms. As a digestion exercise to myself, I sought to write this explanation with relatively little use of algebraic geometry in a manner that minimizes the amount of miracles required, although there are still a few places where some remarkable phenomena occur. And then going through a little bit about, kind of thinking over the solution here. Let me get to the end here. And he really kind of susses this out, I think. Okay. Okay, so just kind of working through, and of course he works through this using an AI chatbot. I've used an AI chatbot to discuss various aspects of this problem and to confirm several of the calculations made here. So he works through this whole thing himself in the AI chatbot, and really kind of, seeing maybe the pros and cons of the solution. And then there's some comments here, and I'm not going to get into the mathematics of this because I'm nowhere near being a mathematician. So this is just kind of the debate in the field. So the point here is that there's this sort of debate in the field about how large language models approach mathematical problems and how they solve mathematical problems. So that's kind of where we are with this. So anyways, the summary of this Terence Tao article is that he described the construction of this proof as appearing like a massive miracle, highly unlikely to be located by brute force. And so this counterexample is one of in a string of recent mathematical accomplishments of language models, consisting mostly of them disproving open conjectures. Another such example is the unit distance conjecture, which has been open for around 80 years. So last year, several language models achieved gold medal level performance on the International Math Olympiad competition. This person wrote a short thread about it, reflecting on what it meant about the relationship between symbol manipulation, reasoning, and intelligence in humans and machines, and arguing the developments aligned with the paper we wrote about symbolic behavior in AI. This was a paper that this person and colleagues wrote, Symbolic Behavior in Artificial Intelligence. And so this is just on the arXiv. The ability to use symbols as the pinnacle of human intelligence, what is yet to be fully replicated in machines. Here we argue that the path towards symbolically fluent artificial intelligence begins with a reinterpretation of what symbols are, how they come to exist, and how a system behaves when it uses them. We begin by offering an interpretation of symbols as entities whose meaning is established by convention. But crucially, something is a symbol only for those who demonstrate or demonstrably and actively participate in this convention. We then outline how this interpretation thematically unifies the behavioral traits humans exhibit when they use symbols. This motivates our proposal that the field places a greater emphasis on symbolic behavior rather than particular computational mechanisms inspired by more restrictive interpretations of symbols. Finally, we suggest that AI research explore social and cultural engagement as a tool to develop the cognitive machinery necessary for symbolic behavior to emerge. This approach will allow for AI to interpret something as symbolic on its own, rather than simply manipulate things that are only symbols to human onlookers, and this will ultimately lead to AI with more human-like symbolic fluency. Okay, so this is kind of the basis for this discussion as well. And thinking about how AI uses symbols, and of course mathematics is a lot of symbolic processing. I concluded last year's thread by noting that there's still a big jump from competition math to systems that could meaningfully contribute to progress in mathematical research. But things have been moving fast, and I'm excited to see how they continue to develop. So that was last year in the thread on this paper. Since now it seems that AI can really make progress on long-standing mathematical problems, it seems like a good time to more fully expand these reflections on symbols, neural networks, and the nature of intelligence and mathematical understanding. So there are a couple of points that are going to be articulated in this post. The first is thinking about classic symbol manipulation. And that classic symbol manipulation is not an innate part of human cognition. Instead, it is something we learn with effort. Because of that, it is very often useful for humans and neural networks by extension to use external symbol systems, such as programs, as tools. And by doing so, we can learn to internalize approximation of these systems. Number three is that it is the very flexibility of neural networks that allows them to learn both regular and irregular structure that makes them effective in such a broad range of problems. The points above, 1 through 3, have been part of the connectionist view of neural networks since the beginning. So this is all part of this connectionist view, or the classical connectionist view, thinking about symbol manipulation and how humans use symbols. And so these themes then are central to understanding AI's recent progress in mathematics, where even though the core aspects of the field are classically symbolic, the process of mathematical reasoning reaches beyond symbol manipulation. To quote Paul Cohen, who's a Fields medalist, one must essentially forget that all proofs are eventually transcribed in this formal language. In order to think productively, one must use all the intuitive and informal methods for reasoning at one's disposal. So not just thinking in that stilted sort of symbolic system and its consistency, but just thinking in any way you can. And this is where the effectiveness of large language models comes into play. So in this post, I'll talk about the history of symbols and neural networks in cognitive science, discuss forays into mathematical cognition, and return to recent contributions of AI. So thinking about sort of the dawn of connectionism and the things that led into the dawn of connectionism, we have to go back to very early AI. And so before connectionist research started exploring neural network models of cognition, we used something called GoFi, which was symbolic in nature. These kinds of systems perform syntactic manipulations over symbolic structures, such as production rules, or logical inferences over logical expressions. So if you go back to Newell and Simon, they hypothesize that this type of classic symbol manipulation is the necessary and sufficient means for general intelligent action. And of course, this idea fell into disrepute once connectionist models really got rolling, and there was this divide between sort of symbolic models and statistical models. However, trying to make generally intelligent versions of such systems proved challenging in practice due to issues like the frame problem, which can be defined as the difficulty of constraining the explosion of propositions that such a system could possibly make about any action to just the important ones. So basically, if you have a set of rules and a set of propositions, you keep generating new exceptions, and you end up with so many things to evaluate that it's hard to kind of find the most important ones. So in parallel, the connectionists started to see the ability of neural networks to modeling aspects of cognitions, focusing on perceptual problems that were challenging for symbolic systems. So thinking about which parts of cognition were not well served by this sort of symbolic approach. So in particular, the parallel distributed processing of neural networks allowed them to do things like using context to constrain inferences and resolve ambiguities. This is, I guess this is chapter 7 out of some book. This is Modeling Cognitive Processes, the Interactive Activation Model. So I don't know what book that is specifically, but they talk about PDP modeling techniques in that article. Okay, so, but the connectionists also saw the potential of these systems to go far beyond perception. For example, acquiring the syntax and semantics of language, and one of the first applications of what might now be called a causal language model that predicted one word to the next. So this is very early on. The connectionists thought, oh, this might be a great, we might be able to simulate language in the way that we're doing our building our models. This, we could call it a causal language model that predicted one word to the next. It maybe even have the capability to reason. So this is 40 years ago in one chapter of the parallel distributed processing books entitled Schemata and Sequential Thought Processes in PDP Models. I guess this is the, let me see. Okay, this is this book, Parallel Distributed Processing. So I think that's where the other article is from. I'm not going to get into this article because I don't have permissions, but this was from Rummel, Hart, Smolensky, McClellan, and Hinton. This was chapter 14, Schemata and Sequential Thought Processes in PDP Models. The authors directly engage with the origins of human formal reasoning by external symbol systems. The passage I highlighted, and I'm not going to show the passage, this passage here, succinctly articulates a series of ideas that I would restate as follows. So the first is that humans are not inherently particularly good at logic, but we are good at finding patterns. So, using sort of logical propositions to model human behavior is folly. You want to look at pattern finding and pattern identification. Number two is it is therefore useful for humans to externalize symbol processing through writing symbolic equations. And so, this is what's useful, what's heuristic. And to state what thought is, you externalize symbol processing. Number three, this allows us to achieve certain systematic inferences, such as mathematical results, by a series of simpler steps to which we can readily see the solution. And number four, this is, of course, cognitive offloading. And we're offloading things into these environmental tools like mathematics or like symbolic systems. And this is the real symbolic processing. And this is, in fact, the primary kind of symbolic processing that humans do. Number five, by learning through using externalized symbols, not internalized symbols, we can then learn to internalize approximations of these systems. So if you write down a set of equations, you can then internalize those and approximate from those systems or reason from those systems. So if I show you a proof, you can reason from that proof. If I can't show you a proof, if I'm just communicating what's internal, then it's harder for you to reason from it. And it's harder for us to share that information, reason from the same source. So in simple cases, this can obviate the need to actually use the external versions after learning. So we may not need to use the external versions. If we know everything that's going on, we can do it from memory. An important part of expertise, even for domains like science, engineering, or math, is precisely the ability to see patterns, allowing us to make efficient inferences. And so I will argue that this set of ideas closely approximates the way that current AI systems engage with mathematics. So this is Rage Against the Connectionist Machines, and it's about the Fodor and Pilschen critique of connectionism. And so Fodor and Pilschen rejected connectionism, and they argued that it seems indubitable that cognition is syntactically systematic. For example, that it is impossible for humans to understand one sentence and not understand another syntactically equivalent one using the words they know. They argued that this systematicity was due to the compositional structure of human mental representations. So, for example, that we represent a sentence in a way that combines our representations of its components in a way that preserves their structure. Since syntactical symbol manipulation systems were a natural way to achieve such compositional systematicity, Fodor-Ampelchen concluded that the only way that connectionist models could model higher-level cognition models would be as a mere implementation of a symbolic process. These arguments, together with similar ones from others, drove a long-standing trend to dismiss neural networks as only capable of modeling simple perceptual processing rather than real higher-level cognition, which is both symbolic and systematic. For example, while data-driven neural network-based AI algorithms effectively model machine perception, symbolic knowledge-based AI is better suited for modeling machine cognition, or the right move may be to integrate deep learning, which excels at perceptual classification, with symbolic systems, which excel at inference and abstraction. So this is just kind of a thought about kind of the Gary Marcus approach of, or the thing that he advocates, which is, of course, neuro-symbolic systems. Now, one might think a potential merger on analogy to the brain. Perceptual input systems like primary sensory cortex seem to do something like what deep learning does, but there are other areas like Broca's area and prefrontal cortex that seem to operate at much higher levels of abstraction. Like the earlier advocates of symbols, these perspectives suggest that what's going on in the brain to make intelligent inferences is fundamentally symbolic processing, and that neural networks are not suited to these types of inferences and perhaps just to perception. So, of course, there was a connectionist response to Fodor-Ampelchen, basically refuting that argument. A couple of points there is the first one is that the putative symbolic structures of human cognition are sometimes helpful, but often misleading approximate characterizations of the emergent consequences of the real underlying processes. Then, of course, the benefits of connectionist models include their ability to capture graded structure, such as the quasi-regularity in exceptions to the English past tense conjugation, not just rigid symbolically specified structure, so it allows us to innovate and to capture irregularities in the language structure that aren't captured by just throwing a bunch of symbols up. Like in mathematics, you have a more formal symbolic process where everything is really kind of highly regular. And in fact, natural language is a lot of quasi-regularity. And then third, the systematicity of human cognition relative to neural networks is often overstated. So even adult humans might achieve only 70 to 90% agreement with systemic generalizations in real empirical tests when they are taught something novel. Hence why external symbol systems that can support human reasoning are useful. So this last point is important to the context of mathematical reasoning. And then what he talks about here is that he brings up some personal experience with the fallibility of human mathematical reasoning. And so, this is something that he sort of derived from his experience as undergraduate teaching math classes, and even advanced smart students, people who are pretty well versed in their field, often struggle to correctly apply things that they had learned previously in a domain like calculus. So domain transfer or transfer of training was very hard, even for the experts. The other thing he noticed is that different ways of presenting things often helped different people to understand. So cognition plays a key role in mathematical reasoning, and in particularly non-symbolic ways. But it's not just regular humans with limited mathematical experience who are fallible. Even professional mathematicians often make errors. Daniel Witt has another nice thread about a series of errors in the published literature that he and his collaborators discovered while trying to prove a theorem. Indeed, the Jacobian conjecture itself has become somewhat infamous for the graveyard of flawed attempts to prove it. This rate of expert error as a strictly symbolic domain seems surprising if human reasoning were indeed built upon classic symbolic reasoning, the type that is guaranteed to be systematic. And so he mentions here that he mentions actually Saunders MacLean's work on mathematical reasoning and how mathematical reasoning is driven by intuition. Symbol systems are tools that act outside of a language model. So again, we have to think about symbol systems being sort of outside the domain of a language model, but part of this cognitive ability that they have. So with that perspective, let's return to AI and mathematical reasoning. I think that the progress in AI has largely followed the perspective the connectionists outlined. In particular, the generality and performance of the systems on the IMO actually improved by removing strict symbolic structure built into the system. In 2024, DeepMind system relied on reasoning with the lean symbolic language. We talked about this earlier. And using the language model simply to guide its research. This system required manual human formalization of the problems. Even with this additional help, it only achieved silver or medal level performance. However, the following year, a system that reasoned end-to-end in natural language achieved even better, gold medal performance, removing the constraint that reasoning be strictly verifiable in terms of steps, and actually improved overall performance. This allowed the model to write correct proofs to more problems, while leaving the proofs relatively readable at the end. And so this year, similar systems are making progress on problems that mathematicians have not yet solved, thus conveniently avoiding the common claim that the progress of language models is simply due to memorization. We don't know the full details yet of how these proofs were achieved, but we do know from the announcements that both the Jacobian and unit distance conjecture results were achieved by general purpose language models, not specifically designed to solve math problems. These systems probably wrote equations or even more programs along the way. They may have also used symbolic solvers for formal verification of the result. But that stage, I argue, is irrelevant for the cognitive issues as originally discussed, just as when a human mathematician uses any of these tools. Indeed, everything I have described is deeply in keeping with the connectionist perspective I outlined above. And so, it is useful for both humans and models to sometimes use external symbol systems as tools for thinking and verification, both in learning. So DeepSeek Math V2 version 2 is an open source effort at this. But in either case, the intelligence that drives the proof is not a classical symbol system. Instead, it is the intuitions and ability to see patterns and paths to solutions that are key to effective mathematical reasoning, abilities that general purpose language models have started to emulate. And then this is just kind of going this last part here. Thus, while there have been various attempts to reinterpret the recent successes of language models in mathematics, it's really about the success of neuro-symbolic methods. I think that this should not be interpreted as any sort of victory for symbolic accounts of cognition itself. Instead, I think that recent research is clearly following the vision that connectionists laid out originally, that classic symbol systems are useful external tools for an intelligent system to use, but that those symbol systems are not the intelligence itself, even with higher level human cognition that behaves more like a neural network than a classical symbol system. External symbol systems can be partially internalized in such a network, or in humans through effortful practice, but even if they remain fallible or graded, I think a much more faithful description of how mathematical reasoning proceeds in both humans and language models than Forder could imagine. So this is just kind of rebutting a lot of the critics of connectionism in terms of this distinction between symbolic systems